Welcome to 8.2. We're going to continue our discussion of relations by talking about three key properties in relations, namely reflexivity, symmetry, and transitivity. So we're going to talk about, is a relation reflexive, symmetric, and transitive? So let's look at an example to kind of illustrate this. So again, we're going to use the set. A is 2, 3, 4, 6, 7, 9. And we're going to find the relationship A that for any pair of xy, x is related to y if 3 divides x minus y. Well, the nice part about division here is that it's going to actually work great, because if you look at 2 is related to 2, and 3 is related to 3, and everything's related to itself, that's one of the key first things we can notice. Also, 6 is related to 3, and 3 is related to 6. And similarly, 3 is related to 9, 9 is related to 3, 6 related to 9, 9 is related to 6, and 4 and 7 are both related to each other. So if we were to draw a diagram, again, those directed graphs, we would get this wonderful thing here. So let's look at this and let's see what are some properties we notice. Well, one, notice that every single point loops back to itself. Okay, that's really cool. There's not a single one that doesn't have a loop on it. Okay. The second one is, let's look at here. 4 goes to 7 and 7 comes back. Okay. 6 and 3, there's an arrow going both directions. That's really nice. Lastly, if I have 3 of them, so like here, 3 goes to 9, which goes to 6. So there's an arrow from 3 to 6. So in other words, if I have a path between 2 of them, path I can work my way through, I just go to a shortcut. There's a shortcut exists. And this kind of triangular idea is the idea of the 3 ideas of reflexive, symmetric, and transitive. Namely, reflexive is everything is related to itself. So it's reflexive if the relationship automatically be reflected for itself, and it's symmetric if x is related to y, then y is related back. So the first one was the loop one. Reflexive is the loops. Symmetric is the two-way, where there's if it goes one way, it comes right back. And transitive, this idea that if A goes to B and B goes to C, then A goes to C. This is an idea that we knew in logic, and we liked in logic for if-then statements. We can also write it like this. And it's the exact same idea, but it's all how you want to look at it. If you want to look at ordered pairs, or if you prefer to look at them as the R relationship. So we have these 3 key properties: reflexive, symmetric, and transitive. And again, I'm repeating them 3 times to make sure you get this idea. In order to be reflexive, every element has to be related to itself. To be symmetric, anytime one element is related to another one, it has to come back. So let's go back for a second to this diagram. So notice 2, let me get my little hover thing. 2 is not related to 3, so I don't have to worry about 3 being related to 2. So because 2 is all by itself, it actually satisfies it. 4 is not related to 3, so we don't have to worry about coming back. But 4 is related to 7, so we do have to worry about that coming back. That's the key idea here, is that these things are going to build up, and we have to look at them. So let's look at something that is not reflexive. That means there's at least one thing that is not related to itself. To be symmetric, there is at least a pair of elements that x is related to y, but y is not related back. The transitive, I just have to find a triple where x goes to y, y goes to z, but x does not go directly to z. So this whole thing, and by the way, it doesn't have to have all 3. It could have 2 of them, it could have 1 of them, it could have none of them. So let's look at a couple of relationships real quick, and let's talk about them. Are they reflexive, symmetric, or transitive? I'm gonna do the R. That's the first really, really big one. And my question is it reflexive? So the first off, to do reflexive, I'm going to look at the ordered pairs and And notice I have A, B, I have 1, 0, 1, 2, 3. So I need to have 4. So for this first one, I'm gonna need 4. So I have 0, 0, check. 1, 1, check. 2, 2, check. 3, 3. So is it reflexive? It is, because it has all 4 of those. The end. What about, is it symmetric? So let me get rid of all of those for a second. We have reflexive. All right. Now, if I come and I say, okay, I have 0, 1. Let's just look at this one. If I have 0, 1, I have to have 1, 0. I do have that, so that's good. I have 0, 3. I need 3, 0. Boom, I got it. And since the other pairs that are not clicked are all the reflexive pairs, we're actually already good. So this one is symmetric. So now this is where it gets kind of, now we have to start doing a dance. Is this one transitive? How would we do that one? Well, this is actually where it would come in handy to simply draw a little picture. So again, we have 0, we have 1, we have 2, we have 3. 0 goes to 1, goes back. 1 goes to, and I'm gonna drop the loops just for a second because I'm not worried about the loops. 0 goes to 3. So the question is this transitive? And the answer to that is no, because notice I could follow this path to get from 1 to 3, but there is no path here. So this one is a no. So when we drew the picture, we can kind of see that that triangle was incomplete. And that was the key thing that kind of helped us out. All right, go ahead and pause the video, and I want you to answer parts B and C. Go ahead and pause the video and do those. All right, so if you did that, let's just talk about these things real quickly. Is S reflexive? Well, it has 0, 0 in it. But does it, and it has, but notice, is there a 2, 2 or a 3, 3 in there? No, there's not, so it's not reflexive. Is it symmetric? The answer is no, because while it has 0, 2, it does not have the reflexive, the symmetric version of it, which is 2, 0. And is it transitive? Well, to kind of draw the picture, I have 0, 2, and 3. 0 goes here, 0 goes here, and he, look, I have a path that I can do this, and then I have the shortcut. So yeah, I do have a triangle. It is in fact transitive, but it's not symmetric or reflexive. And the last one is none of the above because it does not have any of the reflexive pairs. It has 0, 1, but it does not have 1, 0. And actually, you could say, I take it back. It is transitive because let's just draw a picture again of it. So for T, my bad. I just realized as I was saying that, I was explaining my different. We have an arrow going this way. And here's 2, here's 3. But because I don't have any half triangle, I don't have like 2 steps, it is actually reflexive. It's not transitive, it's not reflexive, but it is transitive. So here we have S and T are both examples of transitive relations that are not symmetric or reflexive. And A is an example of a reflexive symmetric relationship that is not transitive. All right. Let's continue our topic, but let's switch up from doing these small sets to infinite sets, because now we can't just look at all the examples. So the last example, we could literally draw it. This is where it gets kind of funky and hard. So if I'm looking at a massive thing, my question is it reflexive or is it symmetric? And again, remember, it breaks if we can find something. Well, just like proofs are more general. And so just because we cannot find something doesn't mean it doesn't exist. We have to kind of explain it in more general sense. So let's talk about this. Reflexive means it has to be reflexive for everything. So if R equals X, it's kind of the idea where it's true, but that's only true if I'm using the equivalence relationship. So this is why equivalence is true, because everything is equal to itself. Symmetric, if X is equal to Y, then Y is equal to X. The transitive, if X equal to Y and Y equals Z, then X equals Z. We know that these are actually things we've done your entire life. And it's actually because equivalence is a perfect relationship. In fact, we call this an equivalence relationship if it satisfies all three. So what about the less than? Is it reflexive on the real numbers? Well, take any two real numbers. If X is less than Y, let me rephrase it. Is X less than X? No. Easy, zero. Zero is not less than zero. One's not less than zero. There's a whole bunch of examples. We can break, it breaks all. It's none of them are reflexive. But all I need to do is one counterexample. Is it symmetric? That means remember, if X is less than Y, then Y. So in order to be that, this has to be true right here. If X is less than Y, then Y is less than X. That is not possible at all. So again, just need one example. 1 is less than 0. I mean, 0 is less than 1, but 1 is not less than 0, so it's not symmetric. Again, you only need one example. What about transitive? So for transitives, if X is less than Y and Y is less than Z, then X is less than Z. So it turns out this one is transitive by the transitive order of the real numbers. So the real numbers are ordered in such a way that they actually have the transitive property, which is why we get this. But that's not always true for every single thing we'll deal with and other situations. So just be clear that it's kind of hard to explain in many of these situations, but there is a way to have done this previously. And there's actually a more technical definition and proof, but I'm not going to get into it. Let's do another one. And I want you just to pause and think about this one. So this is the relationship that we started off with, except we did it on a small set. So we're going to let M be related to T if 3 divides M minus N. Is this reflexive? Is this symmetric and is this transitive? I want you to pause the video and answer all three of those questions for yourself. All right, so I'm hoping you actually did that. And let's follow through on each of these steps. So is it reflexive? Yes. But it's because if you take any value and you minus itself, it's going to give you 0, which is a multiple of 0 or divisible by 0. Hence, it is reflexive. Is it symmetric? Well, this one's a little bit funkier. So let's think about this for a second. Suppose it's true. Let's suppose the M and N are integers for which this is true. Is it true that's this way? Well, if M minus N equals 3K, then N minus M equals negative 3K. Or in other words, if I multiply both sides of this equation by -1, it will turn this side into N minus M and this into negative 3K, or K times -3. And exactly that, we have solved it. Here's that walkthrough. Again, remember, to reverse the order of subtraction, we only have to multiply by a negative. So because of that, multiply both sides by a negative to keep the equation balanced. And it turns out that that's 3 times a negative K, which is still 3 times some integer. So boom, we found it. So it is indeed symmetric. What about transitive? Well, this one's a little bit harder to write. So if I have this N minus M, we can actually break it down. We're gonna say, let's suppose that there's 3 integers where 2 of them are true. So we have the M to N and then the N to P. The question is, does M go to P? Well, the way we do that is we simply look at, well, if m goes to n, then it's equal to 3 times some r. And n minus p is equal to this. Well, how do I deal with this? Well, notice if I add these two lines right here together, the m, it's going to end up with m minus p because the n's are going to end up canceling out. So I'm going to end up with this, where we can see that m minus m plus n minus p, the n's are going to cancel out. I still get m minus p. And we have 3r minus, sorry, 3r plus 3s, which is 3 times r plus s. So that's clearly a multiple of 3, or it's divisible by 3 by definition. Therefore, it's transitive. So this was a little bit harder because we couldn't just brute force all the examples. We really had to think about how to manipulate it and explain how this will always hold true because we want this property. Turns out transitive properties are actually a really, really powerful thing. We love transitive properties. They're super powerful. And so as a result, we also want to talk about something called the transitive closure. So a relationship obtained by the least number of ordered pairs to ensure transitivity is called the transitive closure of relationship. And one of the things to point out here is this. So if I have a relationship, the transitive closure is a superset of that. In other words, it's going to have everything in R plus some extra. So, but it's going to be the smallest amount of things I have to add to R. So you start with R and you start saying, what do I have to add? So let's look at an example of this. Let's look at A is 0, 1, 2, 3, and R is relationship 0, 1, 1, 2, 2, 3. So visually, what's that look like? Boom, it's this. So we want to find its closure. Right now, it's not transitive because I can go from 0 down to 2, but I need this extra one right here. So I need to add this extra line. So if I add this line, so let's just start working on that. Let's add this extra line right here. Okay, now I can also go from 1 to 2 to 3. So I need to add this line here. So we're adding lines each step to take care of it. But now notice I can get to 0 to 3, but there's no direct line from here. So I have to add one more line going down. So just like this, by adding these arcs, I've actually created a transitive graph by adding 3 more pairs. Now notice 1 can go to 2 and can go to 3 and then go directly to 3. There is nothing, 1 does not have to go to 0 because it's not the way we built it. So we actually have designed here a transitive thing. Hence, this is the transitive closure. So we just have to think about each of those transitive situations. What do I have to add little by little? Let me know what questions you have. Good luck. Have fun.